Hello, my name is Devin Dijkstra,
And my name is Christian Ball.
And I am Connor Rolfs.
and this is our word ladder solver project. So first of all, our code is on the right here, and if I just export it, it'll start to run. So the first thing you'll do is try to import all the words from a file.
Now, to explain how that works, it reads in the dictionary file, which is separated out using enters and new lines to denote new words. And when generating, it uses asynchronous generation for each length word, meaning that it will generate individual graphs for all different lengths of words. Now, when actually generating the graph, it will add new words one at a time and check for differences between the added word and all other words already existing in the graph. If the differences are 1, it will be assigned an edge weight between those 1 for 100. This is done to allow 2-letter jumps, however, to highly discourage them as well, so that when searching using a weighted algorithm such as Dijkstra's, it will prioritize 1-letter jumps over 2.
You were breaking up when you were saying that the 2-letter jumps are weighted with 100 and 1-letter jumps are weighted with 1. Yeah, that's the only thing that you missed there. All right, so and we can actually use Dijkstra's algorithm by using the search command. So if we just do a standard search, let's do a long one of atlases to that one's 45 steps. So care to explain how that works?
So in this case, there are no 2-letter jumps. So that means that it's going to forego Dijkstra's algorithm and instead use a breadth first search, because in the cases where there's only 1-letter jumps, it is essentially an unweighted graph because all the weights are 1. So basically, it's a breadth first search implementation that uses a few quirks specific to this project, such as using maps to map strings to integers in order to indicate the distance between two nodes. And basically all it does is return a vector of the word path, which is then used by the function to output it.
Yeah, and while you were talking, I generated one that does require 2-letter differences from cabbage to
And
brownie.
for ones that require two-letter differences, if they exist, then it uses Dijkstra's algorithm in order to determine the shortest path between the source word and the destination word. However, the Dijkstra's algorithm will always prefer to use as many 1-letter jumps as possible before resorting to a 2-letter jump.
All right, and the last function of our code is the actual output, or the render output. So if I just render 0 right here, it will output the word traversal of cabbage to brownie. Now this does take about a minute to do, just because it is a very large image, and there's a lot of nodes. So I'm just gonna show what we pre-rendered. So here we have our traversal. It goes from green to red as it traverses through the graph. So, oh boy, I think it's here where it starts cabbage, and then somewhere is brownie. Oh well. And 2-letter jumps are shown with a dashed line to show that they are weighted less than the solid line, weighted more than the solid lines, and to discourage. There we go. That's where brownie is. If I exit out of this, is it done yet? No, not quite. Once that is, I'll show that it is different because it is randomly. The nodes are randomly placed each time. So that's our project. Thank you very much for taking your time to listen to us, and I hope you have a great break. There we go. So it took 87 seconds, and that's this one. So cabbage to brownie. And the image is different because it was just rendered. There isn't just a vertical dashed line, now it's diagonal here. So there we have it. Thank you very much. Have a great day.